I'm Mr. McBrien. This is TEJ3M Circuits, Predicting Logical Output. So yesterday we talked about the logic gates and Boolean logic and how to represent these things. Today we're going to dig a bit deeper. We're going to relate algebra to circuits, so to give us the capacity to go from algebra to circuit design and from circuit designs to algebra. And then we're going to talk about how to predict the behavior of the circuits that we design. So as a quick review, here are the gates, the most important ones for today. Make sure that you know that this is an AND gate, this is an OR gate, this is a NOT gate. And when we talk about these, this will give us enough information to be able to discuss the construction of circuits. Now the symbols for this, the dot represents AND, the plus symbol represents OR, and the bar over a character represents NOT. So we knew this as of yesterday, and we could, based on a simple algebraic expression, construct a correct circuit. But once we start adding circuits, we get to the question of how do we construct this more complicated combination of components. So if we consider this A, or B, and C, the big question is essentially, where do we put a bracket? Where do we, which gate comes first? We can have the OR gate first, or we could have the AND gate first. And you can see that there is an interpretation of our expression that can give us either one of these circuits. And you might ask yourself, does it even matter which one we construct? Does it matter which order we put these in place? And to get that answer, what we can do is start to look at the idea of extracting the output from a circuit. And we do this by taking the gates that are on the left-hand side, the ones that get the inputs first, we predict their output, and then we put their output into the next gate. So we follow it along in essentially a linear fashion. And doing this, we can compare the output between our two possible designs. So here's our truth table for the circuit on the left. And using a series of tricks we're going to learn, we can see that the output for the first three cases is 0. And after that, it kind of alternates 1, 0, 1, 0, 1. Now, if we set up the other circuit and we do the experiments to set the inputs and measure the outputs, we get a slightly different result. You can see that in the case of A high, B, and C low, we get a different result. Similarly, if A is high and B is high and C is low, we get a different result. Clearly, the two circuits are not equivalent. So now the question becomes, which one's right? And really, this is the topic of today's discussion. How do we go from algebra to circuits accurately? And if we have something like this, A or not B and B or C, the question is, how do we construct a circuit for it? By extension, of course, we're saying, how do we predict the output for it? But we'll get there. Okay, so let's unpack this a little bit. What we wind up doing is having to create an order of operations, just like in mathematics. And in fact, when you take higher level Boolean algebra, you'll see that the symbols were chosen carefully to kind of match order of operations and make them work a lot like mathematics. So our order of operations, NOT expressions go first. So we consider this NOT B to be the first gate we're going to deal with. After that, just like in mathematics, brackets come first. After that, AND operations come before OR operations. Now, logic circuits are normally shown left to right. If you ever construct them right to left, it's going to raise a few eyebrows. No great reason for it, but it's how we typically do it. Okay, so what we can do now is we can use these rules to create a schematic for our expression. Now, if you want to, you can draw these by hand, but Schemit, the circuit drawing tool that we saw, the free online tool, will also let you draw schematics for Boolean circuits. So what you can do is work left to right, and you can insert the gates based on the order of operations. So we know that NOT goes first. So the first thing that we do is recognize we're going to need B twice. So we're going to branch it. We create a NOT gate here, so we now have the input of NOT B, but we're going to need B as well for this other term, so we branch it first. So NOT B is in place. Next, we do the brackets. Now we can do these simultaneously. All right. So we can do the brackets simultaneously, so we can put the gates on top of each other. So on top we have A or NOT B. That's this one. And on the bottom we have B or C. And finally, we do the AND gate next. And then of course we have our output. So let's try another one, maybe a little bit more complicated with a few more rules built into it. So once again, we do the NOT gate first. After that, there are no brackets, so we don't do any brackets, but we recognize that there's an AND gate, so we put the AND gate in place, this being NOT B and C. And finally, we have the OR gate. Sorry, not finally. So then we have our OR gate, A added into the equation, so to speak. And then we have our final OR gate with B coming into play. Now, in terms of getting the output from these things, in terms of generating truth tables for more complicated expressions, we already saw the truth tables are pretty easy if we have a single gate. It's just based on logic. But as our expression gets larger, it gets harder and harder to predict the result. So what we do is we introduce new variables at the output of each one of those intermediate gates. And we'll modify the truth table, adding columns for the additional variables. And as we do this, we can label our schematic with these new variables. Okay, that may have sounded a little confusing. Let's see how simple this can actually be. So let's take a complicated expression, might look familiar, and say, okay, how do we predict the output for this expression? If we just simply took our truth table and individually looked at the inputs, it could get very hard to get our head around each one of these, predicting the output for Y. So instead, what we do is we add variables. We rewrite the expression stating that Y is actually equal to E and F, where E is equal to this first bracket and F is equal to the second bracket. And those, of course, are just the outputs from these two OR gates. So we can label E and F on the outputs for the gates. And so we can take our truth table now and we can add in columns for E and F. And F is really easy to predict. It's just B or C. And so we can quickly predict the outputs from these because it's a simple OR gate, just examining B or C. But E is a little more complicated. Remember that E is actually equal to A or not B. Well, some of you might be able to do that based on examination very easily, but in fact we can make it even simpler. We take our intermediate gate and we say D is equal to not B, or the output from here. Now, E is a simple OR expression. it is A or D. And we introduce one more column to our truth table. D is equal to not B. E is equal to A or D. And again, this prediction is very easy to do. And you should see that it's now trivial to get the final output of y equals E and F. And you should be able to do that by examination fairly easily. Okay, so there is how we can predict the outputs of our Boolean expression or our circuit, depending on how you want to look at it. We could do it by expanding our truth table. But there's an additional way we can do this. So there are simulators available which will essentially let you build the circuit, change the positions of the switches to match what we're testing, and look at the output. And logic.ly is pretty cool. It's a free demo and lets you construct circuits and generate the outputs. So you can populate that truth table just by changing the positions of these switches. When you hit one that actually has an output of high, the light bulb turns on. So this is a pretty fun way to verify your capacity to build circuits and also verify that your truth table is correct based on your predictions. Okay, maybe that's enough for today. So our key points: the order of operations is important in creating circuits from algebraic expressions, and especially in predicting the output. NOT gates are done first. They're followed by NAND and NOR expressions. Brackets are usually used to prevent confusion. So we can add brackets around any expressions if we need to make it clear what we're doing. And if we want to accurately predict the output of a system, we're going to start introducing new variables, adding columns to the truth table to make it easier to predict. Okay, the references for today. Have a look at www.logic.ly and try out the free demo. You don't need to download the software. And using that, you can complete the Boolean circuit simulator activity homework. Thanks very much, and have a great day.